In the previous video, I began talking about the conditions for valid inference in multiple regression. Let's go ahead and continue that discussion. We're now at the fourth sub-bullet down here, right here, the conditional distribution of E is normal. E is our residual, or error. And so we need to have a normal distribution of residuals. So how do we check for the normal distribution of residuals? Well, if we call back our notebook here and let's put in another code chunk, and let's take a look at how we can determine if we have normal residuals. I'm going to paste in a command. This command is asking us to obtain from our beds income model, asking us to obtain our standard, which stands for the standardized residual. That is, we're obtaining z-scores for all those residuals. And then once we have the standardized residual, we can use that in what's called a QQ, or quantile plot. And we're going to use a normal quantile plot. And so the function I'm using here in R is QQ_norm. So I'm taking my output from the R standard command and I'm putting it as input here for the QQ_norm, and it provides something like this. Now, one final thing that will make it easier for us is to, again, if we can put a line up through there. And so we're going to use a quantile line. And so that's a QQ line command, and it will superimpose a line on that graph. All right, now we got to talk about what this means. So here are basically the z-scores for those residuals that we observe. So if you look at any single data point, let me start with this one up here in the upper right because it's kind of by itself, and so it's going to be easy to talk about. If you look at that data point, we have a residual score for that data point of, it looks like, over 3. It's a z-score of over 3. Now, what is down here is what we would expect the z-score to be for each of those points if they come from a normal distribution. So notice here, we're a little bit over 2 is what we expected for that point, but instead it is over 3. So that's not fitting very well with what we would expect for a normal distribution. This line represents what we would get if the sample observed values, that is our z-scores for our residuals, matched up perfectly with what the z-scores would be like from a normal distribution. Then those points would be right exactly on the line. Well, just like in anything in statistics, it's never going to be exactly on the line. If we look at simple linear regression and we have a strong correlation, you still don't get everything exactly following a line, and the same will be true here. But I will tell you that up to about a theoretical and a sample value of 1, which is right about here, up until there, it looked good. It looked as though these residuals were from a normal distribution. But once we get beyond that point, we're actually getting higher z-scores than we had anticipated getting, meaning that our residuals are getting excessively large in terms of the largest residual values that we find. We would not expect them to have z-scores as high as they are. So that's telling us something about the tail, the positive tail of our distribution is extending out further than what we would expect from a normal distribution. There's a positive skewness that is occurring there. Now the lower end, does not look like what I'd expect with a skewed distribution where it's all compact in. We kind of start out looking like, trying to describe it when in fact I could just draw a picture. We kind of start out looking like, oh, it's going to be a normal distribution. It's going to be a normal distribution. But then we end up tailing off. And instead of coming down like the normal, like we'd expect, we end up with these higher z-scores out here. So the QQ plot talks to us about our residuals. Now, if you think about when you did inference in your first statistics course, when you were looking at inference for the mean, inference for proportions, we relied a whole lot on the central limit theorem. And what does the central limit theorem say? The central limit theorem says that if you get a big enough sample, even if your original data are not normal, that the sampling distribution for the statistic is normal. Is the same true here? Good news, yes it is. What is the statistic we're estimating? Well, it's actually a variety of statistics. It's all those coefficients. We ended up having, in our model, we ended up having an intercept plus 2 explanatory variables. So we have 3 regression coefficients that we're estimating. And it turns out that the sampling distribution of those regression coefficients, those sample regression coefficients, remember a sampling distribution is a distribution of statistics, so the distribution of B0, the distribution of B1, the distribution of B2, we need those to be normal. And if we have a large enough sample size, then in fact we will have normal distributions for those coefficients. If we had a nice QQ plot here where everything fit along the line, we don't even need a large sample size because it would say our residuals are normal. Very much like what you learned about the mean. If you draw from a normal distribution, then you can make valid inferences about the mean. And if you don't draw from a normal distribution, you better have a big enough sample size. Well, how big is our sample size here? Our sample size, we have 53 observations. Should I use rules like more than 30? I actually probably want to have even more than that. I probably want to have more than that, maybe more than 50, maybe even more than that. Again, it's rules of thumb, but remember we're dealing not just with a single statistic, we're dealing with 3 of them here, B0, B1, and B2. So I wish I had more than my 53 that I have here. Now there are rules of thumb out there you can find about how many you should have, and some say 50 for each of your coefficients, some say 30 for each of your coefficients. The problem with the rule of thumb is it depends upon how far off we are from normal. So in this case, we're pretty good, except a little bit here up at the high end, we've got that little bit of skewness that I talked about. The more heavily skewed the distribution was, the bigger the sample size I would want to have. So I might be kind of playing around on the edges here with do I have enough observations with these kind of data for me to have a normal sampling distribution for each of our coefficients. And I know that sounds a little loosey-goosey. You would like me to have real hard cut and fast rules, but it really does depend upon your data distribution. What do we do if we don't meet these conditions for valid inference? Well, what I do is I go ahead and do the analysis anyway, but then I would warn my readers that my intervals, my confidence intervals, my p-statistics, is all of my inference is an approximation, and it's not nearly as close as I would like it to be. So maybe I'm saying 95% confident, but I'm really not 95% confident. That's really the way I handle that. Again, I wish that I could tell you that this was all clean and neat, but it's not. And doing statistics in the real world is not always clean and neat. All right, so let's look back here at our conditions for valid inference again. What do we have here? The last one, the explanatory variables are measured without error. What, you ask? A variable that's measured without error? Isn't every variable measured with some degree of error? Yeah, with quantitative data especially, you're going to expect some error. So what does this tell me? That I should never do multiple regression? Well, it's kind of telling me that if I want my multiple regression to be perfect, I'm going to have perfectly reliable measures, and I probably don't. So right off the bat, before we ever start doing our multiple regression, if we have measures that are not perfectly reliable, we've not met the conditions for valid inference. And so as a consequence of that, we're always going to have a bit of an approximation going on, but statistics, as I've already said, is approximate anyway. And this also warns you that if you start getting very unreliable measures, you probably shouldn't be delving into this kind of statistical analysis. I always say that the statistical analysis part is the easy part, obtaining valid measurement that are reliable and telling us what we're giving us data that we actually can use to make informed decisions. That's the hard part. So if someone tells me I've got measures that are pretty close, not a whole lot of error, if one of my explanatory variables was height, which is seldom the case in behavioral research, but to use that as an example, you'll understand. My error of measurement is going to be because I don't read that ruler just precisely exactly right, but I still feel pretty comfortable with those measures. Well, if I can find the same sort of thing with achievement or aptitude or motivation, then I can treat it the same way. One final thing I'll say before we move on to the next video, in which I'm going to talk about the reasons that we need all these for making inferences, is I want to ask this question. I'm asking it rhetorically because I'm going to answer it myself. And the question is this: what about if you don't have any of these conditions? What does that say about your regression equation? And the answer is that your coefficients do not actually rely on these conditions. Your coefficients are maximum likelihood estimates that are that don't rely on these conditions in order to be accurately estimated. What you're worrying about here with many of these conditions for valid inference is you're worrying about how those estimates, how they vary. That is, what the sampling distribution looks like, what the variation is of these estimates from data set to data set. But for any given single data set, you can go ahead and calculate a regression model, and you have calculated a regression model that is the right thing for that data. It's just that you'd like to extend beyond that data. So those are really two separate issues. Is the regression equation itself valid? Yes. Are my inferences valid? That's another question, and that's where we need these conditions. All right, why do we need those conditions? That's the subject of my next video. I'll see you there.